Professor Deb is right now in Indian Association for Cultivation of Science. He did his PhD from there, and then subsequently he was in Israel with a very well-known researcher, Professor Podusky. And he moved to physical research laboratory where I had a strong overlap with him. In fact, both of us belong to the same group, which eventually became quantum optics and quantum information, with Professor G.S. overall as the leader. Then Bimalendu moved to cultivation again. So he leads a very active group of researchers on this light matter interaction, cold atoms, different kind of sort of light matter interaction in realistic systems, molecular systems, how to manage things with light, photo association, varieties of things. So today he is now here. So you can start speaking.
Thank you, Prashant. It's a great pleasure to participate in this conference, and it's remarkable that it is running for a month, and I participated a few of them. I could not attend all of them. So thank you very much for inviting me, and thanks to all your team members. So let me share my screen now. Okay. Can you see the screen?
Yeah, we can.
Okay. So now I can begin now. So the title of my talk is Exploring Quantum Information by Atom-Atom and Atom-Ion Cold Collisions. The way I have planned to present this talk is the following. First, I will discuss a little bit about EPR paradox. All of you know that it's Einstein's Podusky and Trojan paradox. They wrote a paper in 1935, which is a landmark paper. And the quantum information, in fact, or quantum...
Sorry to interrupt.
Okay.
It's blinking sometimes. I mean, just it's coming black and I don't know. It's a problem for everyone or not, I don't know.
Maybe so. I maybe for a moment I can leave and I join again.
Yes, rejoin, please.
Rejoin. Okay.
So there is some issue. Actually, it was blinking. I mean, the same black and white is coming.
Yeah. See, when you stop speaking, it immediately blinking stopped. Let us see. Let him join back again.
Yeah.
It's blinking quite a bit.
Okay.
Hello?
Yeah, it was blinking quite a bit. Yeah. I mean, it is his network issues because he couldn't join.
Yes.
Sorry about this. Now, Alok, can you hear me?
Yeah, yes.
So
Please share the screen.
Okay.
Yeah, it's okay.
It's okay?
Please make it full screen.
Now you can see?
Yeah, I can see, but yeah, it's not blinking now. It's okay. Yeah.
It's okay.
Please go on.
So to start with, I will begin by discussing the famous EPR paradox. It's okay?
No, it is because of maybe you are making it full screen. That's why. Because when it was not full screen, it was not blinking.
Okay, so maybe.
Yeah, this is right. It's not blinking.
Okay. Now I can share screen. One moment. Now it's okay?
Yes, yes. It is fine.
Okay. So the reason I chose this EPR paradox because it's the original proposal was based on a collision model. So I thought it's more appropriate to give a brief introduction to this famous paradox. It is no more a paradox, it's a resolved issue. So that's why we have this quantum information science these days. And I will discuss two-particle entanglement in translational and spin degrees of freedom. We are very much, all of us, familiar with the entanglement in spin degrees of freedom, but one can generate hyper-entanglement both in translational and spin degrees of freedom. Then I will discuss the various platforms for quantum information processing to give a broad perspective in the field. Then I will discuss quantum gates by cold collisions. Then I will discuss basic physics of low energy collisions and how to control atom-atom cold collisions by external fields. Here, external fields may be a magnetic field, an optical field, or many other fields. And that will give you a handle to control resonant interactions through Feshbach resonances or shape resonances or Fano resonances. Then I would go to the next topic, atom-ion cold collisions and quantum information processing by control collisions. I put a question mark here because it's not yet realized the quantum information or gate operation by cold atom-ion collisions, but there is some progress in neutral atom-atom collisions. So in the contents, so let me begin this EPR paradox. So what is entanglement? Entanglement is the inseparability of joint wave function of two or more objects or parties or particles, even if the objects are spatially separated with no communication signal between them. So this is a quite counterintuitive concept, and this term was first coined by Schrödinger in the context of EPR paradox. So in 1935, Einstein's Podusky and Trojan paper. So what they thought is this led to an intensive debate about what is called local realism and completeness, whether quantum theory is complete or not. And for the next 3 decades until 1964, and Bell introduced the famous and which goes by his name, what are called Bell's inequalities. And so the theorem of John Bell came in 1964, who showed that if one can construct some criteria whether the quantum mechanics is to test whether the quantum mechanics is complete or not. He formulated some mathematical inequalities, and if in the experiment, if it is found that these inequalities are violated, that means quantum mechanics is right, or if they are not violated, then you have the problem, okay, with quantum mechanics. So this is the first time that Bell showed how to test completeness and realism, what the concept that Einstein, Podusky, and Trojan introduced in the laboratory. So so an unambiguous experimental proof of the violation of Bell inequality was reported in 1980, especially by the experiment by Aspect's group. So now EPR paradox is now resolved. There is no more paradox, so it is not a paradox. One can say that this is EPR theory now. And non-locality is inbuilt in the wave function of an entangled system or entangled state. So to put the things in the proper perspective, let me begin by two particle collisions. So Einstein's, Podusky, and Trojan, they considered a special kind of collisional system where you have and correlations, some special kind of correlations in space and in momentum one can generate by some collisional mechanism. So in quantum mechanics, we describe momentum by this operator, momentum operator, canonically conjugate to the position where operator. So this is given by this. So for simplicity, let us consider a one-dimensional collision. So let us consider this particle 1 and 2. Initially, they are far apart, and they collide head-on. Okay. So, and you see at present when they fly apart, and they become well separated with no possibility of any interaction between them or no communication. So, and what kind of special correlations they carry on with them, here I describe. So consider this is, so what is the momentum eigenfunction? Momentum eigenfunctions, you can write this kind of exponential functions, which are in 3D, these are actually the plane waves. And so what about the position detection? So if you detect momentum of one particle P, then other particle will have momentum minus P, because they satisfy this constraint where P plus P prime equal to 0 all the time. Because they collide at 0 center of mass momentum, and because of momentum conservation, this condition has to be fulfilled for all the time. So these are momentum eigenfunctions, but what about position eigenfunctions or position detections? So if they are in momentum eigenstates, they are no more in position eigenstates according to quantum mechanics, because you have this uncertainty relation between the position detection and the momentum detection. So in this wave function, all positions are equally probable. So that means you can you can create a superposition state in all momentum states. And since momentum is a continuous variable, so you have to integrate over this momentum eigenfunctions. So this is a position eigenfunction of the operator x1 with eigenvalue x. So this is how it is written. So this is about single particle wave functions. So what about these two particle wave functions? If you consider two particle momentum wave functions, then this is a function of x1 and x2. Then you have to integrate, because this p prime plus p equal to 0. So you integrate over this p, and then by using this delta function, so you can easily see that this phi x1 becomes this delta of x minus x1, and this phi x2 minus x0, and x0 is the separation between the two particles. So in this kind of wave functions, two particle wave functions, if you carry out measurements on momentum of one of the particles and also the position measurements in the same particle, and that appear considered in their paper. So what is that?
There is no sound. Bimalendu, there is no sound. Hello?
Bimalendu, you are not audible.
Whoever is managing, there is no sound.
Bimalendu, unmute yourself first.
Okay. Oh, sorry. So what I was discussing is the Gadankin experiment that Einstein, Podusky, and Trojan considered in their famous 1935 paper, that let there be measurements on either of the
Sir,
particles.
I'm not sharing the screen.
Oh, sorry.
You have to share the screen, Bimalendu.
Now he has gone. Yeah.
Prashant, tell Bimalendu to share the screen.
Yeah, I'll do that. I'm just sending one message. Yeah. Bimalendu, are you speaking? Still not audible.
Bimalendu, unmute yourself.
Sir, we are not able to hear you.
Can you hear me now?
Yeah, we can hear you.
Sorry, I don't know what is. Now you can see the screen?
Yes, sir. Yeah.
Okay. 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 So I was discussing this. Okay, then this is the paper I was referring to. What is a physical reality according to Einstein, Podusky, and Trojan? So a sufficient condition for reality of a physical quantity is the possibility of predicting it with certainty without disturbing the system. So then question naturally arises, what about uncertainty principle of quantum mechanics? So uncertainty principle applies to physical quantities described by two non-commuting operators. What EPR argued that uncertainty principle is fine for single particle wave functions. So one can construct, as they have shown, a class of two particle wave function for which the principle does not hold good. So EPR concluded that either the description of reality given by the wave functions in quantum mechanics is not complete, or these two quantities cannot have simultaneous reality. This is their statement, but what we know that they can have simultaneously, because you have to then apply the uncertainty principle over the entire wave functions, although the two particles are separable. And here, what I was discussing, that what the way they constructed this problem, and then they thought this Garankan experiment, that if you measure the first particle either momentum or position, so if the result of momentum is p, then you will know certainly that the other particle has momentum minus p. And similarly, so if the position of particle is x, then you know that the other particle is x plus x0, because the separation between the two is x0. So what conclusions are drawn from these measurements? By the way, can you hear me now, Prashant? Can you hear me?
Yeah,
You can hear it.
Okay. It is so silent, so I thought again I am disconnected or not. So what conclusions are drawn from this measurement? It is possible to know exactly or with arbitrary precision both the position and momentum of a particle, even without making any measurement on that particle or without disturbing it. So then the question arises, since the momentum and position are two canonically conjugate variables, what happens to uncertainty principle, which lies at the very foundation of quantum mechanics? So the quantum mechanical description of reality given by the wave function is not complete. So either one is true, or when the operators corresponding to two physical quantities do not commute, the two quantities cannot have simultaneity. This is their conclusion. But then Bohr came in and he strongly argued in favor of quantum mechanics. Now quantum mechanics is valid because it's even though they are separated, it's a common wave function. So wave functions can be non-local. So it is shown that a certain, what is his statement, the criteria of physical reality formulated in recent article, Einstein's Podusky, contains an essential ambiguity. So he disagreed with what their argument, that there is ambiguity and it is applied to quantum phenomena. In this connection, a viewpoint termed complete complementarity is explained, from which the quantum mechanical description of physical phenomena would seem to fulfill within its scope all rational demands of completeness. So there is essentially the question of an influence on the very conditions. This is his argument. The quantum mechanical description of reality given by the wave function is not complete. So then Bohm's
Prashant, is it completely disrupted? Should I join later? Prashant? Prashant, are you there?
There, trying to come back.
Completely disrupted.
Bimalendu is there. I don't know.
So you may have some internet problem or something.
Yeah.
Okay, give me a call in case it resumes. Okay, please.
Yeah.
All right. Yeah.
Yeah.
Sir, please unmute yourself. You are muted.
Okay, now you can hear me?
Yeah, we can hear.
Okay, so there is a huge impact of EPR and Bell's works. So entanglement has emerged.
Sir, sir, please share your screen. It is.
Okay. Now you can see. Can you see?
Yeah, it is visible.
Okay. So my computer is too slow. It is. So, but.
Well, we lost you on the EPR paradox slide. This is, I think you are going forward. You need to go back, maybe.
Okay.
You need to go back. I'll stop you.
Okay. So
even before you were explaining this EPR paradox. That is why we lost you.
Here.
Before.
Next.
This is the page. This is the page where we lost you.
Oh, this is the page. Okay. So, okay. Sometimes what happened? Okay. So
you are talking about the 2-point wave function. From there you can start.
So this is a special kind of correlated pair wave function where total momentum remains zero, or center of mass momentum remains zero all the time, and there is a position correlation which is delta correlated positions. So if you can produce such kind of correlated two pairs, and if the two partners of the pair are separated enough, Even so, then if you measure one particle and with certainty, you can predict the other particles. But the fallacy in this argument is that you cannot do such kind of measurement. Measurement has to be formulated in a different way because they share a common wave function. So whenever you measure one particle, it's not actually a measurement on one particle, it's a measurement on two particle state. So this is how the API paradox is resolved. So is this okay now? Is this clear? This argument that the locality is ruled out, a correlation can be non-local, and it's the quantum mechanics allows this. So this is how this paradox is resolved. Okay. So then, David Bohm, he extended this idea of translational entanglement to spin entanglement, and he argued that this could be tested, although he considered Gedanken experiment. But after John Bell, the scenario changed, because before John Bell, it was more like a philosophical discussion and debate. But the John Bell first showed that it could be tested quantitatively. And this is how he formulated that instead of just measuring the two separated particles in two spin directions, but you can, in two measurement, you can do it in three ways. By rotating the polarizers, and one can formulate an inequality which is testable experimentally. And so, Professor Shubhashida, is this okay now? I can continue with my talk. Various platforms for quantum information processing. So then,
everything is fine.
so there is then it has sparked new research fields that entanglement is emerged as a resource for quantum information after the aspect experiment showing that conclusively showing that the Bell's inequality is violated to a maximum amount, and so. For quantum information and quantum communication, so then there is teleportation, quantum metrology, quantum computations, quantum information and entanglement can be used for these processes, and manipulation of the superposition of states of qubits and their entanglement. This leads to what is the field, the new field called quantum technology, and so this quantum technology will use quantum gates and quantum processors. So these are well connected, these areas, and fundamental in the context of fundamental science, a new way to treat many-body physics from quantum information theoretic point of view, and there is a new quantum chemistry emerging that where one can ask the question, what is the role of quantum entanglement in chemical processes, in chemical reactions, and so on. So requirements for successful quantum information processing or quantum communications. So Senjo gave 5 criteria. These are well-known criteria that you should have well-defined qubits at your disposal, and those qubits should be scalable, meaning that if you increase the number of qubits, you should be able to do computation or quantum processing in a large scale. So an initialization, one should be able to initialize the system in a unique pure state. And then the qubit should have long coherence times. That means when you have superposition, the lifetime of the superposition should be large enough. So that is the coherence time. How long a superposed state can live, that gives you the coherence time. And then one should have universal set of quantum gates, and these are single and 2 qubit gates. And qubit specific measurements for readout, whatever processes you do, computation you do, you should be able to read out. Okay, everything is fine. Okay. So among the most popular platforms, one is, and the mostly used platform is the superconducting circuit QED for quantum computation. So they seem to satisfy all the criteria reasonably. So that's why we have some success in the Google computer, the superconducting computer, or many other laboratories are trying to build superconducting circuit QED based quantum computer. So there is ion trap quantum computer. So there is some prototype demonstration, but scalability is an issue in that computer because when ions are charged particles and they lead to micromotions and some other problems. So this is an issue. So neutral atoms in optical lattice, this is also proposed, and these neutral atoms in optical lattice, they satisfy this criteria 4 and 5. No, they satisfy all the 3 criteria first because you can have well-defined qubits in neutral atoms, hyperfine quantum numbers in the ground state manifolds, and you can choose 2 of the hyperfine quantum states, and you can then, because these are in the ground state manifold, so you can have long coherence time, and one can initialize those states by applying some external fields, some radio frequency or Raman pulses. One can generate, or by optical pumping, one can produce the atoms in a unique pure state, and they have long coherence times. But this criteria, universal set of quantum gates and qubit specific measurements, these are some issues one has to resolve in case of neutral atoms in optical lattice. Then neutral atoms in designer lattice, optical tweezers, one can generate many tweezers and arrange them in tweezer in periodic arrays or in some designer optical lattice. And this is a way out to fulfill the criteria, because then this why in optical lattice this qubit specific measurement is a problem, because typically in an optical lattice the lattice spacing is half of the wavelength. So then measuring the qubit states optically is a problem, because typically the Gaussian beams have larger width than half of the wavelength. And so it is a problem to address individual qubits in an optical lattice. But if these are in progress, optical tweezers, so this is coming up is in a big way that one can, in future, one can use optical tweezers for quantum information. So there is then ion atom hybrid system. So that is in the future, which is the object of today's lecture, that I will discuss this whether one can use ion atom hybrid system for for quantum information processing gate operation. But this a long way one has to go to consider ion atom hybrid systems for quantum information processing. So the next topic is quantum gates by cold collisions. So what is quantum gate? Quantum gate is some operations, some like electronic gates, as we know in electronics. They manipulate the quantum states, and quantum states mainly the superposition states. For example, if you consider there are basically two kinds of qubits. One is 1 qubit gate and the 2 qubit gate. So 1 qubit gate acts on a single qubit. Qubit means a spin half particle can be a qubit, atoms prepared in only two-level atoms can be qubit, and there are many other kinds of qubit, but you have to isolate two states of the system, and you should be able to manipulate only the two states of the systems. And so this Hadamard gate is a gate. You can see that this is a combination of these Pauli's operators. So if you have a state in spin half, it will put in a superposition state, or down spin also another superposition, maximally superposition state. Or if you have maximally superposed two states, it will give you a state in up spin or down spin, or upper level, or so this is then Pauli spin operator, like sigma X operator. This is Pauli X gate, Pauli Y gate, just Pauli spin operator, Pauli Z gate, and the phase, it will change the phase of the superposition state. And there is two qubit gate, or there is a target and there is a control. So this is the truth table of the two qubit gate. If both are 0, then it will remain 0. If it's 0 and 1, 0 and 1. But if both are 1, then one state will be flipped to 1 to 0. And there is the C0 gate. You can generate C0 gate in this way. So this is taken from this quantum information book by Barnett. And various systems for creating bipartite entanglement quantum gates, the systems people explored are NMR system, and then cavity QED system. And so one can generate atom-photon entanglement, quantum gates. These are demonstrated experimentally, and photon-mediated atom-atom entanglement and quantum gate. So experiments, one can look at the experiments by Harros and Rempe group and Kimball's group. And Harros received Nobel Prize in 2012 for his pioneering work in cavity QED. Then ion trap also is explored as one of the platforms for quantum information and quantum computing. So Wineland did a lot of pioneering experiments, and he received Nobel Prize in 2012, shared with Harros. And Blatt and many other groups are working on ion trap quantum computing. And photonic systems also, many groups around the world are working. And cold neutral atoms, this is the topic of today's discussion. So in traps and optical lattices, one can consider this as another platform. Superconducting circuit QED, this is the most used platform and most successful, I would say that. So, but this is not the topic of discussion. Other systems, NB center and nitrogen vacancy center, and quantum dots, polar molecules, etc. Any question? Can you hear me?
And then we have stage 1.
Can you hear me? Prashant?
Yes, sir. We are hearing you.
Okay. And so other prospective systems comprising of neutral atoms and molecules are cold molecules. So they have long-range dipole-dipole interactions of polar molecules. It could be magnetic polar molecules or electric dipole polar molecules. And because one can use this long-range interaction nature of the polar molecules to generate entanglement and qubit operations. Okay. And formation of cold molecules by photo and magneto associations has been demonstrated in over the last 30 years or so by various groups. And because direct cooling of molecules is a problem, because one can cool some specific kinds of molecules, but by using cold molecules, and if you associate them and to form diatomic molecules, then one can translationally and rotationally cold molecules. It's easy to produce, but vibrational cooling is an issue here also. Then you have ion atom hybrid systems. So this is just started to be of interest because of experimental. There are many experimental challenge to produce ion atom quantum systems, because this ion atom interacting system is basically a classical system, and you have to cool them to achieve quantum regime. So that I will discuss a little bit. So then atom molecule coupled systems also one can consider. So quantum computation trapped polar molecules, this was proposed by DeMille or in PRL 2002. And so then turning a molecule into a coherent two-level quantum system has been demonstrated by this group in 2019. So molecules are also interesting quantum systems, but one has to cool the molecules to ground state, and because molecules have many degrees of freedom, and one has to isolate only two states of the molecules. That's a big issue. Okay? And control generation and entanglement is important for control interaction between qubits is necessary. This is one condition. So cold atoms as qubits in hyperpoint spin variables or in translational variables are both entanglement. So when you consider the hyperpoint spin in ground state, electronically ground state, so then you have long coherence times in any, because ground states they hardly decay to, and so one has to consider. So that's why people consider this hyperpoint qubits. Right? The translational variables controlling entanglement or quantum information in translation variables is a challenge experimentally also. But one can consider then both hyperentanglement has some utility also. So cold collision is one of the entangling methods that I will discuss in some detail. And quantum information processing with cold neutral atoms, cooling and trapping of atoms in 1980s and 90s has led to the present stage of cold atoms and cold molecules. And this technology of cooling and trapping also led to the development of optical lattices. This is another platform. So you can see that all these new fields have emerged due to the advancement in the technology. If you don't have technology, you cannot think of this. So it is very important to develop experiments and technology for these new areas, what is called quantum technology. So controlled collisions between cold atoms in traps and optical lattices may be considered as a method to generate entanglement and to perform quantum information processing. So this is one of the major topics in my talk. And magnetic, so another tools one can consider the magnetic and optical fresh spark resonances, because when you have controlled collisions and you have resonances and you have control over the resonances, then as Einstein's Podusky and Trojan showed that control collisions can give you entangled states. And so why not this control collision be used as entangling tool to generate qubit or to perform qubit operations. So quantum, so that's why I'm considering also quantum gate operation by cold collisions and trap neutral atoms as scalable systems for QIP. This is a questionable, but one can explore this. So entanglements of atoms by cold control collisions, this in 1999, this group of Jolar and Sirag and many others, they proposed. This is a theoretical proposal in 1999. Then 2-qubit quantum gates may be generated by controlled collisions, and also many atom entangled states in optical lattices. So this is when you have one-dimensional controlled collisions in trap, and by moving the traps and allowing them to interact and collide, so you can uncontrollably, when you have control over their distance by optical traps, then suppose initially this state 1 and 2, then you can have a phase imprinted on that state, and so you can control by generating phase and two particle entangled states. And if you have control over all the experimental parameters in the system, one can do gate operation. So this is one proposal. And quantum logic gates in optical lattices, this is also another proposal by this group, and this is theoretical paper. So this you can see that 20 years back, people have considered this, but experimentally it is yet to be demonstrated. So experimental characterization of two particle entanglement through position and momentum correction. This has been experimentally demonstrated, although it is not a gate operation, but it is how to characterize two particle entanglement through position. So you can see that these translational variables, degrees of freedom, can be used for entanglement generation and manipulation. Can you see? Sorry. So experimental characterization, okay. So this is done in optical lattice. I'm not going in detail, so one can see these references. And then demonstration of neutral atom control, not quantum gate. So this has been demonstrated by, so neutral atom in optical lattices or in optical traps can be used. So this is the proposal that Zoller and Sirac they made in 1999. This is an experimental realization by this group. So control collisions for multi-particles. I can't see my screen. What happens? So why this is so slow? Okay. So now let us come to the next topic. This is basic physics of. So I tell some basic physics about low energy collisions. So cold collisions, collision at low energy. So typically, when what we call cold collision is below millikelvin temperature, cold atomic collisions. And if it is below microkelvin or in the nanokelvin regime, we call it ultra cold collisions. So hyperfine interactions at these temperatures, hyperfine interaction energy scales become important. So you have to consider the hyperfine interaction is the interaction between nuclear spin and the atomic and the electronic spin, because these alkali type atoms, they have, all of them have hyperfine interactions and hyperfine spin states. And some of the alkaline type atoms may not have hyperfine interaction. For example, ytterbium 174, 2 electron system, but here we are considering 1 electron system. So ultra cold collision typically in the nanokelvin regime, And then in that temperature regime, the collisions occur in a few low-lying partial waves. And in the ultra-cold regime, then it is only one partial wave, which is S wave, so it is spherically symmetric. So this follows from the famous Wigner threshold law regime, because from scattering theory, one can derive some laws actually from quantum scattering theory. So those laws state that as you lower the energy, or as the wave number goes to zero, then how the scattering phase shift will behave. So then one can show that only the lowest partial wave becomes important in typical atomic collisions, and all other partial waves, their scattering amplitude goes to zero by polynomially by k tending k to the power some power. So this is the standard textbook one should remind. And so what is this collisional interactions? How does it produce entangled state, and how one can use the control collision for quantum gate operations? So consider this, you have, before the collision, you have incoming state or in state, and this is interaction region. You can consider this is a black box like S matrix. So then you have here out state. So S operating on this, S is an operator. On the in state, you have then the superposition of incoming state and the scatter state. So this is very obvious that scattering at very low energy will produce a two-particle superposition state, because you have in state maybe a different state and scattering state. But so if you have a qubit state here, obviously that incoming state of the qubit and the outgoing two-particle qubit actually. So this can be a two-particle gate operation or something like that. So what is this S matrix? S matrix is the this related to the T matrix by this identity operator minus this, because T is a transition. So transition operator is the deviation of S matrix from unity. So this is, but there is a 2i factor, but one can define it by S minus IT or S minus twice IT. In some of the textbooks, it is defined in this way, or it's some of the 1 minus IT. So this twice, this two factor, you can have some, because this is just a definition. But, so since S matrix is unitary for elastic collision, a quantum elastic collision is intrinsically a process for two-particle quantum state transformation, so quantum gate operation. So this will be useful for quantum inference processing if the collision is deterministically controlled. So cold atoms in traps or optical lattices facilitate studies of quantum state transformation by cold collisions. So this may be illustrated in the following way, that you have for a single channel scattering with a partial of L, then the S matrix element is given by this exponential twice I delta L. Delta is the phase shift, and it depends on the energy or wave number. Then the psi out state would be given by this relation, but this is also, you can write it in terms of T matrix or K matrix. So ultra-cold collision as a two-qubit entanglement gate. So what is the basic idea? So consider collision between two state particles in WTL, means Wigner threshold low regime, that is sufficiently low energy regime, where you have only S-wave collisions, or very low lying partial waves, say P wave or T wave, not many waves. So you can consider this is a quantum collision. So then you have to consider what is called multi-channel collision. So I would elaborate on multi-channel collision, because this is important to understand how one can generate quantum entanglement, and one can use collisions, control collisions for quantum gate operations. So let the particles be indistinguishable. For instance, okay. So let us say that these are bosons, but this is not necessary. They may be indistinguishable. But for the time being, let us consider the two particles are indistinguishable bosons of fermions. So by symmetry consideration, so either even or odd partial waves will be allowed depending on the incident channel state of the colliding particles. So before collision, since we are considering 2 qubits or spin half particles, so you can have 4 possibilities, 4 states. So these are the spin upward, downward, or this this triplet state with the projection equal to 0, and singlet state, only one single. So these are the 3 substates of the triplet. So this is also, these are the before the collision. So actually they are not entangled state, but one can use this Bell basis, or one can make superposition of these states. So these belong to the triplet configuration, singlet configuration. So you have 4 incident channels, and this is the interaction region where collision takes place. So the 2 particles can enter into the collision region in 4 different ways or 4 different states. So these are called channels. So after the collisions, you will have again 4 states, 4 spin states. But then what happens? These states will be superposed. Okay? So the outgoing state, a particular state I, will be superposition of all these 4 channel states. And this superposition coefficient is position dependent. So you can have control over the phase of the system of the superposition states. And so you can see that a controlled collision can generate entangled state in many bases. If you allow only the 2 states by carefully choosing the collision energy, so that other states, other channels are closed. So then at long separation, those states will not be measurable at long separation. So then you can have a 2 qubit state, 2 particle 2 qubit state, which entangled state. So phase can be controlled by external fields, which may include magnetic field or optical field. And this magnetic field tunable resonances are used these days quite extensively for many purposes, for many body physics, and also for many other purposes. And so here we are considering this tunable resonance, what is Feshbach resonance, for making control, for making gates or gate operations. Okay, so this brings us to the next topic: external field control of atom-atom cold collisions. So in order to discuss the possibility of making quantum gates by cold collisions, one has to consider multi-channel collision, not single-channel collision, as I elaborated. So what is this multi-channel collisions, and theoretically how to calculate multi-channel collisional phase shapes and collisional states? So this is important. So we have studied this recently, and we have developed a new method, theoretical method, which is MQDT, which is multi-channel quantum defect theory, using numerically calculated reference functions. I lost some. Okay, this is so some of the basic physics about this multi-channel scattering. So in the multi-channel scattering, then this wave function becomes a matrix because you have several components of the wave functions, but it becomes a multi-component wave function. So then in the Schrodinger equation, in the partial wave decomposition, when you do partial wave analysis, then you can write down the 3D Schrodinger wave equation effectively in 1D wave equation, where this R is just the separation between the two particles. If you consider that the potential, this W is the potential matrix element, depends only on the relative coordinates, not on the center of mass coordinates. But this is not true when the atoms confined in traps collide. Then you have to consider also their center of mass motion. But to keep the things simple, we consider that this is only just in this depends only on the separation between the two particles. So this is a potential multi-channel potential matrix element. So this Wij, this goes as this diagonal terms like this when at large separation R goes to infinity. So this EI at infinity is what is called the channel threshold. So this is the threshold of the. So this you can consider 0 of the energy at any threshold, and accordingly you can scale the energy scales. And so this is the centrifugal barrier. And at long range, then this diminishes this wave function to the
I have a question
higher power of separation. Okay.
How many channels you have to retain in a typical computation or calculation?
It depends on which channels are most important. In principle, all the channels you consider, but then practically or numerically, it becomes sometimes cumbersome to do a large multi-channel scattering calculation using a large number of channels. Then on some physical grounds, you can then, or by considering some symmetry considerations, then you can throw away some of the channels and you can retain only the most important channels. So in case of collisions in the absence of magnetic field, then you have to consider some degenerate channels, then number of channels becomes less. But in the presence of magnetic field, then you have many other channels. But then you have to consider which one is the good quantum number. In the presence of a magnetic field, the good quantum number is the total projection of all the quantum numbers on the quantization axis. So you can then block these channels in block diagonalize this. So then problem becomes a block diagonalize. Then for a particular projection or particular magnetic total magnetic quantum number, how many channels are involved. So you can do calculations using only those channels or retaining those channels. Even then you may discard some of the channels if you see that some of the channels are not so important or the interchannel coupling. So some channels are energetically high enough. So as we are doing low energy collisions, so maybe you can retain only the low lying some channels which are close to the channel of your interest, because there are many channels, but maybe you are interested only one channel, the scattering or collision. Then you can choose accordingly the number of channels in your calculations. Does this answer your question?
Yes.
Okay. So Then what is open channel? So some of the terminologies, because since there are many students, so I should define some of the terminologies, what is called open channel and what is called closed channels. So if the collision energy is smaller than the threshold, lower than the threshold, then those channels are closed channels. And if the asymptotic collision energy, asymptotic means when two particles are free, then what is their relative energy of collision? If that energy is greater than the threshold, then that channel is called open channel. So boundary conditions at R tending to 0, R is the separation between the particles. So on physical ground, at R tending to 0, the two particles cannot reside at the same point. So because there is infinite barrier because of Coulomb repulsion. So at R tending to 0 for all the channels, irrespective of whether a channel is open or closed. And this at R tending to infinity, at asymptotic limit, for if this J channel is a closed channel, then this should go to 0. Closed means it is the asymptotic energy is higher than the collision energy. So at long separation, you want this wave function. This wave function should go to 0. But for open channel, then this satisfy boundary sinusoidal boundary conditions. So for if this J channel has LJ partial waves, so this is given by this. But this you have some freedom. It depends on how you many states, many other kinds of sinusoidal Bessel's functions, Neumann functions, or exponential functions one can use. It depends which matrix you want to calculate. But typically this is in calculations, we use this kind of real functions, sinusoidal functions. So this is the boundary condition for open channel. So subject to these boundary conditions, you have to solve this multi-channel scattering problem or equations. So maybe I have to move fast because I'm out of time. And numerical methods, there is close coupling, the most popular one. In the close coupling, one calculates or one takes all the terms, and this is a brute force kind of calculation. Then there is R matrix, which is developed in primarily in the nuclear physics context. And there is another method called multi-channel quantum defect. So I will discuss this a little bit. And then so each of the methods has some advantages and disadvantages. So So close coupling method is a brute force full numerical method by maintaining linear maintaining linear independence of channel wave functions during propagation of your numerical code through classically forbidden region is an issue of concern. So it's sometimes very difficult to maintain this linear independence because all of these multi-component wave functions, they have to be linearly independent, and in close coupling this is a problem. So there is another called multi-channel quantum defect theory, which is a numerical method. It is actually a semi-analytical or semi-numerical method. And this uses the analytical solution of the long-range part of the potentials. And so as a result, it is applicable to a select class of potentials which admit analytical solutions in the long range. Okay. For instance, Coulombic interactions, Rydberg systems. In fact, this quantum defect theory was first pioneered by Seaton in the context of Rydberg systems. Okay? polarizable or charge neutral interactions. So a pair of linearly independent solutions of the long range potential are known reference functions in quantum defect theory. The wave function in matrix form of the short range part of the potential matrix is calculated numerically in this method. The wave function matrix is matched with the superposition of pair of reference function at a matching point, at a suitably chosen matching point, beyond which these off-diagonal terms, which are actually interchannel couplings, are negligible. No, it is okay. So MQDT, so we have recently developed a new method, MQDT, a new MQDT or multi-channel quantum defect theory. So our motivation to develop an accurate and easy to implement numerical method that is needed to calculate multi-channel wave functions for applications in QIP or quantum information processing by cold collision. The salient features of our method, we calculate one reference function for each channel by backward propagation from the long range by setting the long range boundary condition. The second reference function is calculated by solving Wronskian equation. This is generally not done in multi-channel, in semi-analytical or analytical multi-channel quantum defect theoretic methods. So matching at a suitable matching point is carried out in the usual way, exponentially growing solutions, because you have closed channel, those channels, there are one reference function is exponentially growing, and you have obtained full solutions by matching the two reference functions. So this growing solution has to be eliminated, of the closed channel are eliminated by making a transformation on the wave function matrix. Linear independence of the reference functions is guaranteed in our method. So this is one advantage. The method is applicable to any arbitrary potentials, because if I want to use a code for quantum information processing or to know the quantum gate operation, then I have to make measurements on the output of the collision, on the outcome of the collisions, and then I should be able to predict its quantum states. And so we have to then match the measurements with the calculations. So this is very important. So we have verified our method by reproducing some known Feshbach resonances. The one important aspect is that the implementation of our method is straightforward. So we have any question?
Hey, Bimalendu, can you wind up?
Yes. Okay. So yes, I'm almost okay. So we have verified the S-wave Feshbach resonance of lithium-6. This is experimentally determined, and we have found a good agreement. And this is experimental value actually. This is when this t square goes to 4. And so we have then verified the recently discovered this D-wave Feshbach resonance of in the collision of rubidium 85 and 87, and our numerical results are here. So experimentally, this Singhua group, they produce this D-wave triplet structure. So as they lower the energy, then the broad one Feshbach resonance becomes a 2-peak structure, then there is 3-peak structure. And we have found this, they have found it at 16 microkelvin, 1.2 microkelvin, 400, and we have found this resonance at 37 microkelvin when we do not consider spin-spin interactions, but when we consider spin-spin interactions, and then we can produce a 3-peak structure. So this is then also this ion atom cold collisions. So in ion atom cold collisions, you have several processes. So we have predicted that formation of cold molecular ions by ion atom cold. So ion atom interaction goes as 1 by r to the power 4 at long separation, and this is actually classical collision regime where the many partial waves contribute. This is at 1 microkelvin. So one has to reach this quantum regime below microkelvin regime, and cooling both ion atom at the same trap is a problematic. And quantum gate operation by ion atom cold collision proposed by this group in 2010. You have cold atoms in optical lattice, and you move a trapped ion, and by doing that, one can generate entanglement between and do quantum state operation. So I am at the end. So QIP by controlled collisions. So one can in ion atom system, pulling both ion and atom at the same time is a technical issue because there is a limitation, and the Boletich and they argued that by using high ion atom mass ratio, that is, ion is a heavy mass and atom is a light mass, one can mitigate the micromotion induced heating rate of ion motion in collisions. So following this proposal, recently 2020, this Netherlands group, they have done buffer-based cooling of trapped ion, ytterbium ion, by merging a trapped lithium BEC, ultra cold BEC. So this is about 100 micron separation, and this is ion trap, one single ion, and then one can transport this BEC or the cold ions and study cold collisions between ion and trap. So in conclusions, our suggestions for ion atom quantum gate operation use very low mass single atom in optical tweezer. So optical tweezer, if one can produce deep trapping potential that can be transported into pulse trap. So this may be scaled up to many ions and atoms by using periodic array of tweezers with separation being several micrometers to match the distance between the ions. If you have separation several micrometers, then addressing the qubits or readout is not a problem. So this seems to be possible with currently available technology. With this, I conclude, and thank you very much for your attention.
Questions, open for questions and discussions. So,
question.
Yes.
How many maximum channels they could accommodate in an experiment?
One second, how many atoms?
How many maximum channels they could realize it?
Oh, people have done close coupling calculation using 25 channel, 30 channels. In close coupling,
Not calculation, I'm talking about experiments. How many
calculations, we have done 6 channel calculations, 5 channel, 6 channel calculations. So
that is very difficult, right?
No. In our method, we can include any number of. Then computation time becomes larger. It becomes
reported
expensive.
experiments. What is the maximum number of channels they could accommodate?
In experiments, in low energy collisions, a few channels is in ultra cold collisions. Then 2 channels become important, most important. The lowest open channel and the next closed channel. Because in Feshbach resonance, because this closed channel, there is a closed channel bound state, and when the incident collision energy matches with the closed channel bound state. So people have then developed some 2-channel model to calculate Feshbach resonances. But this has a limitation, of course, so then one has to use, in some cases, multi-channel calculations.
So with the atoms are multi-level atoms like lambda system or V system or something, and you're talking about this scattering with those kind of molecular systems.
Atom molecule collisions is an issue because it's a difficult problem, or molecule collisions. But theoretically and experimentally, people are doing this because this is a developing field, atom molecule low energy collisions, because
Right.
Cooling molecule is a big issue. Is a big issue because.
Okay.
So, but I know that this calcium fluoride molecule is an important molecule for people are considering, and many other diatomic molecules people are considering.
Okay, thanks.
Yeah, Bimalendu, I have a small question.
Yes.
Using this closed channel, open channel, can you think about a quantum memory? Bound state like storage, and you bring it out by changing the potential so that it becomes open channel.
Yes. Then one has to consider atom molecule coupled system.
Okay.
So bound state. So bound state spectroscopy is easier than the open channel, or because so spectroscopically one can detect the states. Because ultimately, if after the collisions, if the qubits fly apart, then you don't have controls.
Correct.
So they should remain trapped. Correct. So this method should be extended to include the trapping, the effects of the trapping potential. So then it becomes a bound state problem, trap bound state problem. Then the question arises: what is the effect of interaction on the bound state wave functions?
Correct.
So that will give you the required information. Yes. On gate on collisional interaction.
Are there any more questions in the chat box?
Sir, I have one question related to quantum image processing. So, sir, I need to do MTech final year project on quantum image processing.
See, that you can send me. I'll answer to you, because this talk is a very technical business. Quantum image processing, you send me an email. To QIQT, we'll answer it. Not a problem.
Okay, sir.
Thank you. So, Bimalendu, thanks a lot.
Thank you very much.
Lot of work. I got updated.
But I'm really sorry about the technique.
No. I mean, see, it happens. Yeah, don't worry. But it's not that bad. 11:35 only. That happens. It's the problem of this age. Nothing can be done.
I have to upgrade my computer.
Yes. So thank you.
Thank you. I see Anirban. Hello.
Anirban is there, and Subhasis. Subhasis, where is Subhasis?
Subhasis, are you there?
Hi, Anirban.
Subhasis is equally absent-minded. He may be lost. Then he will say, I didn't.
No, I'm there. I'm very much there. Okay. So now I have to quit. Okay.
Okay.
I have another meeting to attend. Okay. Bye.
Bye.
Anirban,
বলো
কি খবর?
এই চলছে আর কি।
আমি অনির্বাণ থেকে জিজ্ঞেস করলাম।
বলো, কি পাটনায় বসে আছো?
হ্যাঁ, কেন আপত্তি আছে?
পর্দা গুলো ভালো লাগিয়েছে মনে হচ্ছে তোমার ইনস্টিটিউট।
কোথায় ভালো লাগিয়েছে? আমি নিজের পয়সা খরচা করে লাগিয়েছি।
বলো, ডিরেক্টর ভালোবেসে দিয়েছে।
আচ্ছা, তাই দিয়েছে। সুভাষিতা কোথায়? He is not around, I think.
সুভাষিতা লকড আউট হয়ে গেছে।
না, সুভাষিস ব্যানার্জি।
সুভাষিস ব্যানার্জি।
The next speaker is Subhasis Banerjee, right?
Subhasis Banerjee, আচ্ছা।
Yes.
সুভাষকে ফোন করি নাকি?
হ্যাঁ, করে দেখুন।
number you are calling is currently switched off.
That's perfect.
Subhasis, my God, where is he?
Perfect.
Prashant, can I leave now?
Yeah, no problem.
I have some words. Okay. Thank you very much.
Now we are in sort of the speaker. So. What do you do, my God?
Very good.